Okay. I see nobody has a Four Seasons landscaping background. That's very disappointing.
Rich had one earlier this week.
Yeah.
All right. So I'm going to talk about some work that actually I've been doing together with Arend Hinze really over the last 4 years, but on and off. And, you know, there was some mathematical stuff that I had to figure out. And I'm going to show you some of that things, not the real math, because even though the math, some of the math I had to do that was actually quite hard, but I'm not going to show it to you because there's really no point in trying to advertise, you know, how smart I am, because in fact, it took me 2 years to get there. And I was being dumb almost the entire time until I was not being dumb, which is how it is most of the time. But I do believe that, you know, some really important stuff actually happened there. And so I'm really trying to just get you the gist of it, even though there will be math in there, but the math is actually fairly simple math. It's matrices and ordinary differential equations. That's it. Most of you know that kind of stuff. So let me actually also make a little bit of an introduction in first evolutionary game theory and then stochastic evolutionary games, for those who are not, you know, all the time dealing with these type of subjects. So I wanted to say, I have to figure out, oh yeah. So there's the main concept in evolutionary game theory is, you know, trying to understand how behavioral strategies evolve. And I'm still trying to, okay, I have to figure out where to click. The central concept of that theory is what is called the evolutionarily stable strategy, which is in fact the stable equilibrium point of evolutionary dynamics, where what we're looking at are behaviors, right? And the typical things that people look at as an example are behaviors like cooperation and defection. In order to understand, for example, why is cooperation found everywhere in fact the entire biosphere. But it's still evolutionary dynamics, and in fact the first really standard work on this theory was penned by John Maynard Smith, and it's a very slim book. And if you want a good introduction to the subject, that would be you know, the book to first consult. John Maynard Smith, of course, is a well-known or was a well-known theoretical biologist, and he's actually also well known to people that we know. Here, for example, is a picture of the 1997 Gordon Conference, where you see John Maynard Smith over there, and right to his left, of course, is Rich Lenski, and in fact, next to Rich is Santi Elena. In fact, on this picture, all of these people are well known to people who do you know, evolutionary experimental evolution and things like that. So so it's really part and parcel of you know, how people study microbes, for example. Now, to get to the meat of it, we're going to look at what is known as first as 2x2 games. Basically, it's games where there are two opponents and each has two behavioral choices. If that is the situation that you have, then, you know, what can happen is described by 4 different outcomes, depending on what each of these two players is choosing at that point in time in this encounter. And what this outcome is, in a sense, is quantified in terms of what the payoff is to the player, given the choices that they made. And in this case, with 4 different outcomes, there is potentially 4 different payoffs. Now, the question that evolutionary game theory is asking is, which choice is going to win in an evolving population of players? Like, for example, is cooperation going to win as a choice, or is defection going to win as a choice, as an example? And when we say choice here, this is sort of being used synonymously with this idea of strategy, even though when we go to stochastic games as opposed to deterministic games, strategy takes on a somewhat more complicated concept, but we probably won't even touch on this here, except a little bit later in the talk when we talk about conditional strategies. Now, what behavior is favored, of course, depends on the value of these payoffs. How much money or ATPs or whatever, is the currency of the game, you're going to be getting for the choices that you made. And the way we quantify that is by writing down this matrix, which has these 4 different payoffs in it. And basically, this is the payoff to what we call the role player. This is the role player. And in this case, if my opponent of the role player, which is in fact the column player, if this guy plays A and I play A, then I receive, being this guy, I receive E sub 1, 1. And similarly for all the 4 different outcomes, right? And so you might think, oh, 4 numbers, that's a lot. But it turns out that in many of the situations, actually only 2 numbers are necessary to actually understand the full envelope of the possible dynamics in this population. And in a sense, what we can say is that we can set the diagonal of this matrix to 0. There are exceptions to that, but we'll not cover them here. So we're just going to concentrate on these simplified games. Now, to figure out who wins, well, we have to solve a differential equation, which is here called the Replicator Equation. It's the Replicator Equation because it has no mutations in it, which would be showing up here. If they had mutations in it, it would be called the Replicator Mutation Equation. And we're going to encounter that later. But right now, basically, this equation says that in order to understand the change in the fraction of players in evolutionary time, playing choice A is proportional to the fraction at this particular time, and the fitness of this player, and then the mean fitness in the population. And these are all calculated from these payoffs. So the fitness of an A strategist, of course, depends on how often I'm going to play other A's or how often I'm going to play other B's. And that, of course, depends on the fraction of A and B players in the population. Same thing here for the fitness of a B player. And then, of course, the mean fitness of the population is just the average given the fraction of A and B players of the fitnesses in the population. So if I have all the payoffs, I can calculate everything. Now, let me show you examples of how these fractions can change in the different type of games that we have. And when I say different types of games, it means, in fact, that it depends on really the sign of the 2 values that enter the matrix, namely A and B. Either they're both positive or they're both negative, or one is positive and one is negative. There's actually 4 different games that you can have, right? And so you can actually immediately by sight look at what these fitnesses are if you have such a simple payoff matrix. So that's the fitness A, this is the fitness of B, and this is the mean fitness. And from that, here is your differential equation that is governing the proportion of A players in this case. And if you would like to know what the stationary point, the equilibrium point is, you will be setting this left-hand side to equal to 0 and find out what are the P's that can make that 0. Here's an example. Suppose this is our payoff matrix, okay? In that case, you will find that no matter how many A fraction players you start the evolutionary scenario with, they will all basically go towards 0. So if the A choice, for example, is cooperation, then this type of matrix would tell you that cooperation dies out, no matter how many initial cooperators have. That's actually the prisoner's dilemma, the famous prisoner's dilemma of game theory. Now we can take a look at what this game is looking like by making this face portrait, where I'm just looking at what happens to these strategies depending on where I start with. So we found out that no matter where I start with, I always end up at P equal to 0. So there's a flow on this diagram that always moves towards the defection player. And then you see here, I've sort of made an open point and a closed point. The open point is an unstable fixed point of the dynamics, also called a repeller. And the closed point is in fact the attractor, or a stable fixed point. So we see here cooperation in the prisoner's dilemma is in fact an unstable fixed point, and defection is the stable fixed point. We can also see this directly by looking at the matrix, because if we can look at the strategy's diagonal payoff, if that's higher than the off diagonal term in the column, then that strategy is stable. this strategy, strategy A, for example, the diagonal value is not higher than the off diagonal. So this A strategy is not stable. Here's another example where the payoff matrix looks like this. This is in fact the flow of the differential equation. And we can take a look at the phase portrait, which basically says, there is a stable fixed point at 1/2, and there are two unstable fixed points at 0 and 1. And in fact, we know what the stable fixed point is. It's related to the A and B's. A is 1, B is 1. So it's actually 1/1 + 2. So this is in fact a 50% of each in the population that's stable. And that's the so-called Snowdrift game of evolutionary game theory. I'm going to just show one more just to fill in things. There's also the one where in fact, the interior fixed point is unstable. And so you basically, depending on what frequency you start with, either you're moving all the way to cooperator if you have more cooperators, or you're moving all the way to defectors, and you've immediately guessed that that's the phase portrait that you have in these type of situations. All right, the fixed point is actually the same, except that it's unstable, as you see here. Okay, now that's actually essentially the games that you can have in 2x2 games. I'm just going to show one example of a game where you have 3 strategies, but only 2 players. And that would be rock, paper, scissors. You have those if you have, for example, a payoff matrix that looks like this for R, P, and S. So you see immediately by inspecting the matrix that there are actually 3 stable strategies, because for each one of these strategies, the diagonal point is larger than any of the other in the column. And in fact, the phase diagram looks like this. So you have these 3 fixed points. And if you are at any one of those in the population, you are actually stable. There are others, and that is, of course, precisely what you have in rock, paper, scissors. There are other payoff matrices which look like this. Also a kind of rock, paper, scissors game, but you see that there is no strategy that by itself is stable, because there's no diagonal that is larger than any of the off diagonal points. So the phase diagram for a game like that, which doesn't have any pure strategies as fixed points, it actually looks like this. You actually have oscillations. There is a stable fixed point here in the middle, but in this particular case, you never reach it, but you sort of oscillate. All 3 strategies oscillate around this point. So that's all I wanted to say about the dynamics of deterministic strategies, except I wanted to say that they actually occur in microbial dynamics. So Ben Kerr and collaborators actually investigated that in bacteria, and it basically assigned rock, paper, scissors labels to them, and could see that they are indeed engaged in an evolutionary dynamics that can be described by that kind of mathematics. And that's what I meant by saying that these do indeed describe evolutionary scenarios where the cells are having these payoffs when they interact with each other. In this case, microbial cells. Now, let's move to stochastic strategies. In biology, of course, and that's also true for the game, the biological game that you just saw. Cells, as well as, of course, other organisms, don't always play the same strategy all the time. In fact, they are more likely to play certain strategies with certain probabilities. So, for example, a stochastic strategy would play S with P of S, and it would play P with P of P, and so on. And so there's actually theory that tells you what the fixed points of this type of dynamics is in terms of the probabilities. And that theory says that the fixed points of the mixed strategies are equal to the fixed points of the stochastic strategies. Now that's a mouthful, so let me just show you that as an example. You remember that for deterministic games, you would evolve, in this case, for example, to a population mixture where you have 50% A players and 50% B players. If they now are non-deterministic players, then the solution in stochastic games is that all players will engage in a strategy where this P, the probability to engage in A or B. So 100% of the population in the equilibrium point will play half of the time A, half of the time B. That's what the theory says. So if to recapitulate, so in deterministic games, that was my equation for the population fractions. But for the stochastic games, I'm now basically saying, hey, I would like to know how this probability changes in time. And it's again the same type of dynamics, of course. So here I have an unstable fixed point, and depending on what the mean starting probability is, I'm going to move either of these fixed points. And you see immediately the solution, of course, here. This is the solution for p equal to 1. This is the solution for p equal to 0. And you get, by setting this part equal to 0, you're getting this fixed point. So how do I solve now the stochastic games with mutations? Well, you take your differential equation that you've seen before, and you add a noise term. So now this is a mutator-replicator equation. So what is that noise term? Of course, the noise term is essentially a mutation-driven term that will change this trait. This probability obviously is like a trait. It will change it up and down, stochastically, randomly. So in other words, this is the selective part of the dynamics, and this is the non-selective, the random part of the dynamics. And in physics, we actually know these type of equations, where in fact this noise term, the only thing that you have to specify is the strength of the noise. And you do that by looking at what is the mean correlation function of noise at different time points. And it's basically written like that, where this mu here is the strength of the noise. In physics, it's called the diffusion coefficient, where in fact, where this p, for example, could be a velocity or a momentum or a position of a particle. And then the diffusion coefficient will tell you how often that is being randomly shifted about. And this term here will show you where the mean is being driven to by whatever potential is driving the dynamics. Now, here is this equation. And in physics, it's actually called the Langevin equation. But one of the things that we are interested in is, what is the distribution of strategies in a population? Now, it turns out that to every Langevin equation, there exists an equation that will tell you the time evolution of this distribution function. And that equation is the Fokker-Planck equation. So if we write the Langevin equation in terms of this force term here, that forces the mean towards the point where the derivative of the potential or the force is 0, and then this is here the diffusion or noise term. The associate equation for the distribution function is the Fokker-Planck equation. And it governs this distribution function. Now, let me show you this distribution function. It's basically how in a population, if this is the trait, like for example, in this case, the probability, how is that distributed in the population? Now, in the case of deterministic, in the case of dynamics where there are no mutation, I told you that the winning strategy is everybody has the same P, and that is given by these payoffs. So the distribution function would be like this. It would be just a uniform, or I should say a delta function. Everybody in the population has the same strategy in the absence of mutations. But if there are mutations, then what you expect is a distribution function as the stable solution in time. In other words, you would see that besides the optimal solutions, there are also suboptimal ones, but of course they are less frequent, right? And the width of that distribution is of course determined by the mutation rate. So what can we say about this? Well, this time-independent coexistence of genotypes with different fitness is actually known within evolutionary biology. And it's known as the quasi-species concept that was introduced by Eigen and Schuster in 1979 in this book called The Hypercycle. Now, for those who are already familiar with it, they know what the hypercycle is, but think of it as, having a population not just of self-replicators, but of sequences that replicate other sequences in a cycle, which they call the hypercycle. And what they were interested in is to try to understand the dynamics of such populations at fairly elevated mutation rates. And this is the prediction that Eigen and Schuster are making, and I'm going to show you what this is. This is this relative concentration, which is pretty much what you see over here, as a function of the mutation rate mu in a stable time-independent case. In other words, you solve the equation in the limit that the distribution does not change in time anymore. And what it tells you is that given the mutation rate, you have a stable fraction. So this line here is what Eigen and Schuster call the wild type. It's the one that doesn't have any mutations on it or no errors. So it's the 0 error sequence. At that mutation rate, according to that theory, only about less than half of the population, in fact, is error-free. This here is the frequency of 1 mutants, and you see that it's lower than the wild type, but it's actually a stable frequency. And then 2 mutants, 3 mutants, and 4 mutants, and so on. That's essentially what you see here. That's the 0 mutant, and then there are 1 mutants and 3 mutants at lower frequencies. So this idea of having a stable distribution function is in fact the same thing as Eigen and Schuster's quasi-species concept, that we now are moving towards evolutionary game theory. And the thing to keep in mind about the quasi-species concept is that they are finding that if you have such a group of mutants, then selection actually acts on this clan of mutationally related sequences. While in the low mutation rate regime, of course, you know that evolution acts on individual sequences. Not so, Eigen and Schuster say, at higher mutation rates, evolution actually acts on this group, which they call the quasi-species. And I want to point out that when they use the word species here, they do not refer to the species concept of biology. They refer instead to the species concept of chemistry, because in fact, Manfred Eigen is a chemist, theoretically a chemist. And the idea here is that instead of selection acting on a single species, chemical species, thinking of a molecule as a chemical species, it in fact acts on this group, which he therefore calls a quasi-species. Or you could think of it, in biology, the better term would be a quasi-organism, right? A group. Now here's in fact the Fokker-Planck equation for you. And there's not a lot that you need to really understand here, except that clearly that is the diffusion term, where normally you would have a d for the diffusion coefficient here, and the second order derivative of the distribution function. And if you only had this term, then that would be referred to as the Laplace equation, and you would look at pure thermal diffusion only. This term here has the derivative of the potential in it, so you recognize it as the force term. And if the force is 0, then that means this entire term here would be 0, and you get pure diffusion. So this term here tells you where the mean is being moved to. And if you're talking about fitness, then you're talking here about the derivative of the fitness. So if you're at the fitness peak, then there is no more force acting on you. And then the only force left is the mutational diffusion term. Now, if we are interested in the time-independent solution, we're just setting the left-hand side to 0. And then, in fact, we know what the solution is. And in fact, it can be written in terms of this potential function v as simply e to the minus this potential divided by this mutation rate. And if you come from physics, you immediately recognize this as the Boltzmann distribution, where then mu is actually the equivalent of the temperature. And this is the energy. So in physics, this is e to the minus e over kt, right? And that's the Boltzmann distribution. So what we find is that if we transfer the Fokker-Planck equation to evolutionary game dynamics, we find that we can find the solution, the stable solution of evolutionary dynamics is simply also given by the Boltzmann distribution. Now let's test this. So we can actually test this in that little game that you've seen already. And we're going to use the game where a and b are larger than 0. And then, in fact, from the differential equation, I can write down the potential in terms of powers of p. This is, by the way, in terms of the stochastic game, where these are the probabilities to engage in behavior A or B. So for arbitrary B and A, I can write down the potential, and I can then solve this. This actually is the solution for particular choice in parameters, and it's here for 3 different mutation rates. This is the mathematical solution to the equation. Now I've asked Arendt to simply simulate the evolutionary game theory. And by the way, the fixed point for these values is, of course, 1/3. And when Arendt does the simulation, and this is also the width, of course, given by the mutation rate, which in this case we've chose to be 0.005, what he gets, the theory is actually the one for this case here, that's for a mutation rate of 0.01. The theory sits right on top of Arendt's simulation results. What that means is that indeed, I can now, perhaps for the first time, solve the replicator mutator equation, which is, essentially evolution, analytically, and show that it actually corresponds to what unstable equilibrium I will get. So this is 1 million generations and averaged over it. So you can be sure that it's stable. So great, it works for 2x2 games, but can this be extended to games with more than 2 strategies? And here we are coming to the rock, paper, scissors games. And the disclosure here is that it took me 2 years to solve this because this game is mathematically far more complicated. But this is the game that we're looking at. But instead of looking at this sort of weird game where the entire population constantly oscillates, I'm adding a positive term to these 3 terms, which means, in fact, that you're going to be spiraling down towards a fixed point where the population plays R, S, and P with probability 1/3. Okay, and then the question is, can I solve this mathematically? And it turns out I actually can only solve it in the approximate solution. And I'm going to summarize 2 years of work with a single slide, which you can then immediately forget. So here is actually the equation, which is now a multidimensional equation, because the dynamics actually has these 3 strategies, but one of the strategies, of course, depends on all the 2, because the sum of the probabilities to engage in R, S, and P has to equal 1. As you see here, X plus Y plus Z, the fraction to engage in these 3 different games has to sum up to 1. But the solution is now this multi-dimensional distribution functions in terms of a multi-dimensional potential function phi, and where there are now these forced terms here, which are derivatives of this potential function. This solution now basically is a distribution function over this 2-dimensional triangle. If you remember this triangle, you've seen that before in the rock, paper, scissors. And the maximum, of course, is at the center, at the 1/3, 1/3, 1/3. This is, in fact, the mathematical solution that I obtained. And if I look at just the cross section of that, looking for each of these directions, you're getting that. And in fact, Arendt also checked this, but I don't have the data here. But it actually also coincides with the numerical, with the agent-based simulation of the process up within error bars. So it works also, but the mathematics is a bit harder. In fact, that's an understatement. And I dread thinking about what happens if I need to go beyond games with 3 strategies. So here are the 3 different mutation rate predictions. Now that I have something like this, and I was able to predict the behavior of these type of strategies, let's actually look at strategies that are more complicated, namely strategies that depend on communication, or in this case, on previous play. And I'm going to introduce you to a group of strategies that are called ZD strategies. And what I want to show you is that the winning strategies, if you're playing stochastic games that depend on information or depend on communication, the winning strategies are actually also these quasi-strategies. They are actually better than what other people have called invincible strategies. The only thing, of course, is that these other people that you will meet in a moment, they've only considered the case of low mutation rate. And then indeed, these are invincible. But as the mutation rate becomes increased, the strategies that really win are, and that's not a surprise that you've followed me so far, are these quasi-strategies. So now let me first introduce you to these ZD strategies that I have given several beacon talks with already, but I'm going to just summarize for you what's going on here. So there were these games, these ZD games were actually invented around 2012. And this is sort of a quote from a blog post where it says that the world of game theory is currently on fire because Freeman Dyson and Bill Press have discovered that a previously unknown strategy for the prisoner's dilemma game guarantees one player a better outcome than the other. The way people were basically saying that these strategies could extort your opponent. These were unfair strategies. And I believe I even once called, made references to certain political parties, which I'm not going to make here because this is a science forum. So here is the title of the paper, in fact, which is Iterated Prisoner's Dilemma contains strategies that dominate any evolutionary opponent. Dominate meaning wins, and evolutionary opponent means if the opponent tries by evolution to sort of escape the kind of dominion, it won't work. That was what the paper was saying. Now, a year later, Arendt and I wrote a paper that said, not so fast. And in fact, this blog post appeared, which said the conclusion of these researchers, being Arendt and I, is that winning isn't everything. What we found, in fact, that these strategies that Bill Press and Freeman Dyson thought were winning, they are actually evolutionarily unstable. So let me just show you that very quickly. So these zero determinant strategies are stochastic strategies that select a move, like cooperate or defect, depending on what both of the players previously played. So, and according to this type of strategies, these ZD strategies can manipulate the opponent to accept a fixed payoff, and they can do nothing against that. However, there are not just these nefarious ZD strategies. Later research showed that some of these ZD strategies are actually generous and actually give to the opponent a really nice payoff, as opposed to being mean and selfish. These so-called generous ZD strategies were thought to basically be overall winners, namely that the paper that I'm quoting here is a paper by Alex Stewart and Josh Plotkin. They claimed that it cannot be replaced by any other memory one strategy. Memory one being we only remember the last move, not the last two moves. That would be a memory two strategy. Okay, so here's what they say in the abstract. They say for all but the smallest population sizes, these generous ZD strategies are not only robust to being replaced by other strategies, but they can selectively replace any non-cooperative ZD strategies. And these generous strategies outperform even the most successful of the well-known IPD strategies. And that statement was news to Arendt and me, who in fact had in 2010 evolved strategies that actually win these type of games. And they were nowhere near what these guys said was the winner. So Arendt and I asked ourselves, why is that? So that's the statement that I just said, but we realized that this statement holds only for those, in this case, nice ZD strategies that are in fact fixed points, that are stable fixed points at low mutation rate, the thing that's basically just like one probability. But we can ask, are they also robust at finite mutation rates where fixed point solutions, as you now remember, turn into distributions? Now, what we found is that when we look at these distribution functions, and now we have distribution functions for 4 probabilities because it's a conditional game. So this is the probability to cooperate if I played cooperate previously and my opponent played cooperate previously. This is the probability that I cooperate if I played C and my opponent played D, and so on. So there's now 4 probabilities. And this is the distribution in the population. And except for this gene, the cooperate gene, which is really like a delta function, all the other ones are in fact distributions. And we realized, this is not one strategy. It is in fact a quasi-strategy. This strategy that we found, I mean, it is, you can characterize it by these means, but the means are not the story. The story is that there's a distribution. as I told you, calculating these distributions is possible for simple games. I have yet to figure out how to calculate these distributions for the games with one move memory. Now, this stable strategy that we found, that's actually this general cooperator from the 2010 strategy, and is not a generous ZD strategy. So we can ask, is this generous strategy ZDR that Plotkin and Stewart said was the winner, is this one actually mutationally stable? So we can start a population with 100% of this strategy, which has actually these 4 probabilities sitting here. Okay, that's these 4 probabilities. And then we basically have an evolutionary run and asking, well, what happens to these probabilities? If it's evolutionary stable, then they basically should stay constant over time. But if it's unstable, then they should change. Right? These are the starting frequencies that we seed the population with at a 1% mutation rate and with a population of about 1,000 individuals. And what you see is that while in fact this stay constant, but remember that's actually also very close to the constant in our strategies, all the other ones change over time. This is a line of descent here. And in fact, they change towards the values that we had previously found is in fact the mean values that are evolutionarily selected for, but they are just the means of those distributions. In other words, what Stewart and Plotkin had said was the winner was only a winner at low mutation rate. But if you crank up the mutation rate, they move away and they move towards that mutational cloud of strategies, which is selected for as a group. It's a group strategy. All right, so now we can ask the last question that I'm asking, namely, why are these things, why are these our ZD strategists, which we call the general cooperators, stable, and the ZDR strategies unstable? And to take a look at that, what Arendt did is he basically discretized all these probabilities to create 361,000 mutant strategies that includes wild type, 1 mutant, 2 mutant, 3 mutants, and then had everybody play against everybody. And so the question that we're asking, for example, is if you had 0 mutant strategies, that's ZDR, play against 1 mutant strategies, what is the effective outcome? So this is the payoff that a ZD strategy gets against itself, gets a payoff too. But if it plays against a mutant, on average, it gets a little bit less. It gets 1.7. The mutant itself, if it plays against a 0 mutant, gets a bit more. And this is the payoff on average that a 1 mutant has against the 1 mutant. And if you remember about how you recognize stability in a payoff matrix, you recognize that in order for a strategy to be stable, the diagonal payoff needs to be higher than the off-diagonal term. And indeed, this strategy is stable. This too is larger than 1.77. However, the mutant strategy, its payoff is lower than this, so the mutant is unstable. And if the mutant is unstable, well, then it can't coexist with the 0 mutant. So in other words, they can't possibly form a quasi-species. Now let's check the same payoff for our GC mutant. Here is what we measured, what Arendt measured. And the GC strategy is in fact stable, 2 larger than 1.92. But you see, in fact, that this fitness peak, this is the mutant, is actually very flat. There isn't not a lot of a drop. And if you remember the idea of survival of the flattest, it's of course the idea that you like to live at high mutation rate on a flat peak. So indeed, GC lives on a flat peak, whereas this is a steeper peak. But more importantly, look at this. The mutant fitness is actually stable. The mutant is stable because that payoff is just slightly larger than this. So now we see how it is possible that this strategy actually is indeed a quasi-strategy, is because it's mutant. And then if I extend this to the 2 mutant and 3 mutant, they are all stable, just like Eigens and Schuster's quasi-species theory predicts that all these mutants, of course, are stable at lower frequencies, but they are stable in the population. So that's how that strategy, in this case, they have the same top peak, but you could even imagine that such a strategy could outcompete this strategy if this would be 1.99 or 1.98, just like in the survival of the flattest effect. So indeed, with that, we can show unequivocally that that GC distribution of strategies is the mathematical equivalent of the quasi-species and therefore a quasi-strategy. So let me just go to the summary of what I just told you, which I'm sure if you want to relive it, you're going to have to go and look at that video because I had to speak slightly fast in order to get to this point. Fortunately, we do have a little bit of time, I guess, for questions. So the summary is, in the weak mutation, strong selection limit, that's the limit where one mutation goes to fixation at a time, evolutionary stable strategies are the fixed points of the dynamics. And they are strategies in which everybody is playing the same thing. There are monomorphic clonal groups of strategies. In fact, if you're looking at these famous ZD strategies, in that limit, they in fact rule the memory one strategy space. These generous strategies are in fact the global stable fixed point of this dynamics. However, at higher mutation rates, the stationary solution is in fact a distribution of strategies, not just a single strategies. And for simple games, this distribution actually can be calculated analytically, which to some extent is quite a step forward for evolutionary modeling, because the only cases that you could solve analytically before in the in the limit of finite mutation rates were very, very simplified fitness peaks, where you could actually come up with a mathematical solution, but they were not using the Fokker-Planck equation approach that I developed for this approach. So in that limit, the stationary solution is in fact a mutationally robust quasi-strategy that can beat any of the clonal strategies that you could possibly devise, which is in itself interesting, because if these clonal strategies are certain types of phenotypes that exist in the population, what that means is that in this mutation limit, you can actually have a coexistence, a stable coexistence of different phenotypes in the population, where normally you would saying via the competitive exclusion principle that only one strategy can survive. But here, you have frequency dependent selection, and what it tells you is that you can have a coexistence of different probabilistically playing strategies. A typical example you might be looking at is for a bacterium to engage in a strategy of forming a biofilm, or actually to swim in the population and in its planktonic form. And so you could, this type of mathematics predicts that you could have evolutionary fixed points where certain fractions of the populations engage in biofilm behavior and another fraction engages in swimming behavior, and that the relative fraction is actually a fixed point of evolutionary dynamics rather than the outcome of just random mutations. So in other words, this kind of theory will allow you to attack the question of whether a certain coexistence of strategies is selected for by evolution, or whether it's just a function of mutations existing in the population. So with that, I want to thank my collaborator in crime here, Arendt, who is now a professor at the Dalarna University in Sweden, and who is the one who enables me to do this kind of work, because he can check my theory by doing simulations. And as you know, a theory without somebody checking theory by empirical stuff, is a terrible theorist, because they will always believe their own results. Whereas in fact, you should only believe them if other people checked experimentally whether what you're doing makes any sense at all. So that's why I always say that without that computational component, I won't be able to do the type of theoretical advance that I just showed you. And with that, I think I want to first thank you guys for sticking through all that math and all that talk about evolutionary dynamics, and I can open it up to questions. So, Danielle, you want to handle that?
Sure, we've got a question in the chat already from Mike Weiser.
Okay.
I can just speak if you would prefer.
That's fine.
So I might have missed this, Chris, but I'm a little confused by this statement about how if the main diagonal is lower than the off diagonal, things aren't stable, because it seems to me that it would still be possible for mutants to be stable given mutational pressure. That is, if you have mutations creating the mutant out of the wild type at a rate equal to selection removing them, then of course things would still be stable that way, right?
The answer is that stability criterion is one in the absence of mutations.
Okay.
It's a stability criterion for as basically microevolution of gene frequencies. So you're right, of course, that if you have constant mutations, then you will have coexistence of these mutants that will be recreated. But the coexistence I'm talking about is in fact not that. It is in fact a coexistence that basically is due to the interaction of the selection term and the mutation term. All right. I'm sure there must be other questions, and keep in mind there are no dumb questions in this this arena because that stuff takes really a lot of time to getting used to and wrap your head around, and there's a bunch of equations. But the beauty of this formalism really allows you to separate the selection term from the mutation term very cleanly in that equation, and allows you therefore to think about the two main elements of evolutionary change in a much more concise mathematical framework, namely selection and drift. These are both elements that contribute to how populations change. Are there other questions? I don't have the chat window up because I'm still sharing, but what I can do is I can stop sharing and then I can go to the window where there is a chat. Right, so now I see all the the comments, but yeah, look, well, it's not that long amount of time, but I mean, there's got to be other people that have, even if there's a question that basically something just stumps you about what I talked about very quickly, I'm perfectly happy to recapitulate something so that I can provide more clarity. And otherwise, just feel free once the video is up to just go through the talk at speed 0.5. And maybe that will clarify things that I did not make clear. Else, if you want to ask me a question via email, I'm perfectly happy to react to that. By the way, there is a manuscript in preparation. It has been in preparation for a long time, but I have to now synchronize with Arendt over the ocean to get some of these simulation results. But I'm pretty optimistic that within this month, we're going to have a draft of this manuscript, certainly on archive. And then I will be happy to let people know so that they can read about the things that I have not talked about.
Great, thank you, Chris. Are there any other questions before we wrap up? I will be posting this on the same Google Doc where the schedule is. So if anybody wants to share it or watch it later, that's where it will be.
All righty, then thanks again for listening.
Yeah.
And sorry for imposing too much math on you. But it's Friday night. You're now allowed to have 2 times the number of drinks that you normally have on a Friday night. So it's like my you get my permission.
Excellent. I will take that. Thank you.
very
right.
easy for me to do.
Yeah, for you, yes.
I said drinks. I didn't say it had to be alcoholic drinks,
That's a good point. Hydration
even
is
though
important.
that's literally implied.
All right. Well, thank you, everyone.
Right. See you again next week.
Time.